Good evening, everybody, and welcome to tonight's Origin Science Scholars Program, coming to you by Zoom. My name is Glenn Starkman, Director of the Institute for the Science of Origins, and I'm pleased to be your host this evening. The Institute is a collaboration of scientists at Case Western Reserve University, the Cleveland Museum of Natural History, and other institutions advancing the scientific understanding of the origin and evolution of systems, simple and complex, natural and human, and the applications of that knowledge. And the Origin Science Scholars Program is the Institute's signature public lecture program, bringing origin scientists to the public to discuss their cutting-edge research. I'd like to thank our Case Western Reserve University partners, Siegel Lifelong Learning, the College of Arts and Sciences, and MediaVision for their assistance in presenting this lecture series, and IdeaStream for bringing these lectures to a television audience. Tonight, it is my pleasure to introduce Dustin Tyler, the Kent H. Smith Professor of Biomedical Engineering at Case Western Reserve University. Professor Tyler is Director of the Human Fusions Initiative and the Functional Neural Interface Lab and Associate Director of the Cleveland Advanced Platform for Technology, the APT Center. Please join me in welcoming Dustin Tyler.
Thank you, Glenn. I appreciate it, and I appreciate everybody making a new approach to these unusual times. So this is, I've been given some class lectures, but this will be the first seminar lecture. So let's see how this goes. So thanks for joining. And what I'll be talking about today, what I've been asked to talk about, is this idea of the human-machine relationships. And actually today and next week are going to be a two-part lecture. Today is sort of going through the past to set up where we are and then talk about human-machine relationships in the present, and the particular work that we're doing here of actually realizing new human-machine relationships. And then by the end of today, what I want to do is sort of give you a preview of what next week will be, where we actually think about what we're doing today can expand us into the future and change the way that we think about the human-machine relationship. So let me start. Let's see, there we go. So there's three parts as usual. For this, the beginning is sort of the evolution of the human-machine relationship as it's evolved. The second is thinking about how we want to change that evolution of the human-machine relationship and how we think about it. And then I want to present sort of today's present advanced human-machine relationship that we've been working with, and then give you a preview of what the future is. So when we think about human machine, it's actually, we can go all the way back 2 million years ago when the first stone tools were developed. And since that time, human and its evolutionary ancestors have been developing tools and different types of things, since tools, stones, bones, sticks, clothing, whatever it's been, we've been augmenting ourselves to give ourselves more capability than we would have simply without these. And so that evolution over 2.6 million years has resulted in, so you could say, the evolution of our tools now as cell phones and internets. And the interesting part here, though, and I bring this up, is that when you think about how we used to use the tools, we get on a pointer here. When we used to use tools back in early man's time, we would grab them by the handle, we would swing them, we would look at them. And so even 2.6 million years of evolution of our tools, our interface is still basically the same. The way we work with these tools is we still hold them, look at them, and essentially the same way of interfacing with the tools than we've had before. And so let's think about the evolution of the machine as well. So we can think about the Industrial Revolution as generally thought of in four phases now, where the beginning was the first mechanization, steam power, where we went beyond holding and interacting with tools on our own, but actually creating powered systems that could go beyond that. So steam power, weave looming, up to the point now where we have these massive machines that we can make in the second revolution, if you will, the industrial age, and basically creating these giant machines, new industries, new technologies. In wave three, we started to look at the algorithms in the computer development, right? So how did we begin to expand algorithms? And it's actually about this time when I would say that the relationship with tools, the way we think of them now, began to evolve a little bit. If you think about the revolutions 1, 2, and potentially into 3, or beginning of 3, we were developing tools to aid us in what we're doing. The tool was a tool. As we begin to evolve the algorithms, there became a shift ultimately in what we thought the machines could do. So we began to think of tools in a different light, and it's really become evident, I'm going to present here, that our relationship with the tool became different And in some ways, I want to shift the way we're thinking about it now, but also build on this type of thing. Then ultimately, the fourth generation, if you will, in the revolution, is that everything is interconnected. We begin to get where systems are completely interconnected. The Internet of Things and the Internet is carrying atabytes, 10 to the 21st plus bits of information around the web all the time. And so that totally interconnected started to think about how information is flowing, how we develop algorithms, how we handle information on that scale. And so the other thing I want to point out is that this pace of advancement, the way that machines have been evolving, as they sort of began for 2.6 million years, they were pretty slow. And then really beginning in the last 1,000, 2,000 years, and even thinking about it from 1963 when we think of the cell phone. This is an early ad from 1963, I think from AT&T, showing off the very first cell phone. And what I like about this, and I kind of put it in context for the rest of today and also a week from now, is that this first cell phone was a radio that took up the trunk of the car. It was probably more expensive than the car. And if you think about who you could communicate with, the odds are that there's probably one other cell phone anywhere that could be connected. Nowadays, that everybody has one in their pocket. So in just basically 50 years, 60 years, we've gone from this idea of something that's bigger than the car and costs more than the car to something that's more ubiquitous than people that have power in their homes. And that's a pretty amazing feat in the difference and how fast that evolved. Think about this in the context too, and I just want to lay it out there that if somebody were to present an idea like this, these are the people that get called crazy in many ways. This idea of having a radio takes up the whole car, one tower, nobody's ever going to buy that. But I think the tagline was quite interesting, and I really like this, is outside the chauvinism and the sort of the ideas of the 60s, man getting home at 186,000 miles per second. And that was an interesting idea that they put out there at that time, is that using technology, we can essentially be someplace different at the speed of light. I mean, we became this experience that was data. And this theme you'll see play out through the next two sets of talks that I'm going to present to you. So it's interesting ideas, the evolution, the rapid evolution of change, and this idea of taking experience and digitizing it and expanding it and allowing us to move on to different places. So we've talked about sort of technology and the shift from technology being something we build for ourselves to thinking about it from a big data and how maybe it mimics. And we can see this really even more so in the idea of robotics, where the ideas of robotics have evolved, interesting from say Roombas and devices or even coffee machines that do things for you, to this concept of evolving it towards a humanoid. And I think this is an interesting shift. There's always been this idea since before the times of Newton, this idea of the human automaton. There's been this idea, this parallelism between the human and the machine. And that was sort of in a development. It led to anatomy, physiology. It led to all the things that have become modern medicine in many ways. But as we began to develop the robotics, the idea of a robotic becoming humanoid is an interesting idea. And what it really did is took the human as a machine from the sciences side and said, hey, I can duplicate the human. Whereas in sort of the religion and the other sides created the human as an indescribable and sacrosanct thing. And so these two ideas kind of became at odds with one another, and ultimately in some ways led to this idea of the battle, and if you will, between the human and the machine. And I think what we also want to keep in mind in our current relationship in the technology is building a humanoid robot does not make it human, yet psychologically we begin to ascribe human characteristics to this. And what happens is by this nomenclature and by the way we start to think about things, we create these interesting ideas that I think have been a little too prevalent in today's time. It's something I want to consciously think about a bit. And it's kind of created this idea as we named data analysis, if you will, these chips that were based on human intelligence, the way the brain worked, began to develop these ideas of neural networks and data analysis. But ultimately, we created the term artificial intelligence. We've ascribed this idea of because we use the brain and we mimic the idea of the brain, we're actually creating intelligence. And what's happened is we've begun to create this idea of autonomic systems, robotic systems, which we know are more powerful than us. They've been, if we build them correct, we've been building large machines that are super powerful for a long time. And this idea of calling it intelligence, and we start to say, hey, if I put them together, we end up with this idea of human versus machine. And so, there's a lot of activity that sort of comes now, where you see in literature where we hear of things where the robot is replacing the human, and it becomes this idea of artificial intelligence being more smarter than the human and moving away from us. And this duality, basically this competition, I think, has been harmful to where we're going. Outside of that, the idea of futurist became a new hybrid of essentially science, if you will, but not really, that bred it was a new breed that blurred the lines between science and science fiction. And so people would start to think about the world as it was doing, take data, and then extrapolate. And so rather than just making things up, extrapolation became a fundamental tool and ticket to create broad categorizations of potential futures. And so one of these that you may be familiar with was Ray Kurzweiler and this idea of the singularity, where he started taking the idea of calculations per second and transistors available on machinery and saying, hey, this is starting to look like, if I take the number of transistors and then I equate them to the number of neurons in the mouse brain, we're going to equal that pretty soon. Therefore, our computers are going to be as smart as the mouse brain. And somehow this idea has taken hold, and we have this equivalence of a transistor and a neuron, which itself is a bit off. And then this whole extrapolation idea that we're going to create AI systems smarter than mice in theoretically about 5 years ago. And then eventually about 2025, which is coming up really soon, if you stay on this curve, we should have computers as smart as the human. And what that does is it's describing this idea of the human machine, where the human has the machine has the characteristics of the human and becomes a competitive of who's going to be better. And what I want to say is that this is leading to polarization, right? Which these things grab attention. So we say, hey, a computer is going to beat the human. And that becomes the mantra, is what we tend to do. And this polarization takes hold. But unfortunately, we all know the problem of extrapolation is that it doesn't hold. And so recently in Nature, a couple of years ago, they talked about this equivalent, this asymptote, or this exponential growth, and this already started to level off. Transistors, because physics begin to rule, the curves are bending to physics, right? There's a certain limit that you can't actually maintain a exponential growth here, as well as other things become more important. So power, clock efficiency, or clock frequency, power efficiency, the amount of power you can provide, all these things begin to level off. And so these ideas, unfortunately, well, not unfortunately, but these ideas aren't really holding true. And even in this case, we start to think about the performance of the computational systems. The power per computation is actually really quite small, but now the things like transferring data becomes really important. So the point of all this is that other challenges, so with extrapolation, the ideas induced by the extrapolation become more of a driving force than they should warrant. So the idea of the machine becoming smarter than the human, replacing the human, is actually taken hold when the extrapolation itself is not going to. So now this idea is driving this. And so the idea, not driven by science per se, but driven by an extrapolative belief, can cloud more of the important opportunities and realities that do exist. And so this is really set up in this idea of computers versus brains that we talked about. There's this equivalency that people would create, that the transistor is like a neuron, and that a lot of transistors create these massive computer systems as like a brain. And ultimately, the arguments like Yuval Harari in Homo Deus has said, hey, computers eventually can be greater than the human. Or these are equivalent to the human, that this is the same idea. And so this idea of artificial intelligence nomenclature leads us to problems. And they're not equivalent. And we need to get it, we need to think about the human and the machine not as equivalents in competition, but how do they begin to work together and use the strengths of artificial intelligence, or more appropriately, big data analysis, that humans aren't good at, but machines are. And not thinking about them as a competitive way, but how do we begin to integrate them in more effective ways? There's one other thing that I want to talk about, is the word or the label of reality. The word reality is a question mark here. And so ultimately, we have these things like virtual reality or mixed reality or augmented reality. But we should ask the question, what we haven't asked is, what really is reality? And we'll come back to this idea later, because I think this is really critical when we start thinking about the human-machine interaction and what we can do with this. But we have to ask the question, is this reality, or really transferring information? What's the difference between the two? So kind of in summary, we've talked about the fact that humans created machines to solve limitations in somewhat simple tasks: the physical, size, power, hazardous environments, etc., data, It can store better memory or information better than we can. It can analyze it. Heck, the first calculators can analyze better than I can in terms of doing calculations. It doesn't mean they were smarter. Convenience to do things for us, and connections were basically, this is the interesting piece of, we made connections through audio and visual connections, the virtual reality, but that's 2 of our 5 senses. And that gets back to the reality question and a few others. So we fall into this trap of becoming enamored with what the machines can do better than us. But we wanted to think, and so we started thinking about replacement. But I want to pose to you this idea of symbiosis. We need to think more about this. And so what is a symbiotic system? Without spending too much time, we have these ideas of things that live together but not connected, connected systems, and then actually integrated systems. And they can be mutually beneficial all the way to mutually competitive. And so examples of this are, these worms where the larvae of flies actually consume the worm. Clearly, it's a conjunctive relationship, but the parasite benefits where the other one is harmed. The worm is harmed. And then classic case of symbiosis in the clownfish that lives in the anemone. It eats, keeps the anemone healthy, and the anemone provides it protection. So this is a mutually beneficial, just living together arrangement. People have started to look at this in terms of technology, though, and if you're familiar with the movies from my youth anyway, the Terminator, where this was a purely technological system that supposedly was a humanoid robot that came back, and ultimately created this competitive environment where there was a mutual destruction between the human and the robotic system. So you could say it's symbiotic, it's a relationship between them. But let's shift this paradigm and say, let's look at, so what is technology if we think about it in the context of symbiosis today? And so the types of things that we can talk about here is this competitive way I've been talking, which may be the human versus the machine or AI replacing us, and we get in this who's going to harm who first kind of competition. But reality, AI is mutually beneficial if we use this, for example, in Anat Matabushi and different people that are using intelligence to look at image analysis for better medical analysis or better medical use. For those, again, from my youth, I'm not going to show the larger picture, but these are 7 of 9, which from the Borg. And so she got out of the Borg. The idea was, hey, this is mutual between them, where the Borg itself was a machine taking over the human. Highly beneficial for the machine, not so beneficial for the human. But if we think about today, refrigerators that do all kinds of technology, these are things that we benefit from, but the machine doesn't. Iron Man, which is the idea of Tony Stark, where he would get into a machine, ultimately would both benefit that because Tony Stark's capabilities gave them the machine opportunities, but the machine did not necessarily withdraw from him. So what I want to get out of this is that we're really trying to create this idea of moving from this concept of competitive harm-harm relationship with technology to ultimately a directly connected relationship that's mutually beneficial to technologies and humans. And so this is this idea of shifting this paradigm towards this mutually beneficial symbiosis paradigm.
I see we have one question in the chat box, and I'll take it from there. Dustin, could you comment on the Frontline show in the Age of AI, if you know of that one?
I don't know the details of what comments you would like on that. More specific.
So, yeah, what is how does the common news view of AI, the media view of AI, differ from what you as a practitioner and someone looking at how we're integrating with AI?
Yeah, so that's great. So this concept of AI, the term intelligence is a misnomer, and we sort of ascribe this idea of intelligence or human thinking to artificial algorithms. And they really aren't human thinking. They are data analysis, right? They're statistical methods a lot of times, or they use brain-like activity, or the neural networks are developed around that to do data analysis. But I think what we forget is that this idea of a neuron being the brain isn't quite right. And the idea that we're mimicking the neurons in a totally natural way actually really reduces what we do in our natural brain. So as a neuroscientist, the ideas of intelligence and a psychologist, right? Those ideas of intelligence are far different than a few neurons calculating. It is amazing. And what people get enamored with is how well and how much you can do with a neural network system, with these artificial intelligence systems, but they're not the brain. And so I think if we start to ascribe brain-like capabilities and replacement, I think that's where we start to go a bit awry. And I think what we need to do is continue to say there is amazing things that we can do with these large data set analyses and things that humans actually can't do. But it doesn't mean it's going to become intelligent or replace us. It just means we need to think about this in a much more appropriate way. And so people doing research in this area, actually utilizing it, are understanding that and using its capabilities. But unfortunately, if we start thinking, or I think the negative is when we think of it as a human, it becomes competitive. We're not actually taking full advantage of it. And we get this sort of distancing between us and technology that can become harmful.
Great. So I have another question here from Brian Humphrey. As machines get better and better at production and delivery of goods and sales of goods, will we need a new economy as manual labor and reading medical scans reduces the job market?
Let me just say differently, not reduces, but changes. If you look back in the early 20s in New York, one of the most important jobs was an elevator operator. And in fact, at that point, imagine elevators being brand new and people fearing the fact it's going to take you up 20, 30, 40 stories into these high-rise buildings. That's a really dangerous endeavor, and I'm not going to trust a machine to it, right? And so you had people that basically their job was to operate the elevator, and that was a skill. And at the time, one of the reasons we have automated elevators is that union was so powerful, they basically went on strike and brought down New York, which led to the innovation with an automated system for elevators. You could look back at when cars were introduced, or any new technology is going to be disruptive. It's going to cause a change in that environment. So for sure, I think that as we begin to look at what tasks the machines can do and where the human has to do, I think we need to evolve and think about what is it that we need to do that the machines can't do. Where do we fit in this new environment? So I want to talk about then some work that we're doing. I'm going to tell you a bit of a story first. This is a friend of mine, and basically this person would tell me how one of the things he really enjoyed to do would be to walk out in the park or in the mall or different places with his niece, who is young. I mean, this isn't them. This is just a representative picture. But they would be out walking, and she would always hold his hand. And that had a lot of impact to him. And when I talked to him, he was telling about his work, and he basically was a conveyor maintenance person. He would basically, in industrial conveyors, in fact, it was a laundry facility that he would work and get in there. And one day he was working on one of these conveyor systems, and as he was reaching underneath, working on something, of course, it turned on, or it had gone, there was an accident, and it took off. And all he told me was that for the next 15 minutes, the system was grinding on his arm. Until at the end of this, all he had left was basically just a little bit of attachment to that arm. And he, went in, he tried to replace that arm, he tried or reconnect, he tried to salvage that, not him, the doctors, of course. But at the end of about a three-month period, through infection and problems and continual problems, he ultimately lost that hand. And that's interesting unto of itself. But when I talked to him about what it is that he really misses, now when I began the work that I'm going to tell you about and what we're doing, our thought was that if you lose your hand, you're missing function. You're missing what the hand does, and you want to replace that. When I started to talk to this gentleman, he didn't say function at all in the beginning. And I realized I was quite naive in my initial thoughts, but what he said is the thing that he most missed was when he lost his hand. He continued on. He says his niece was actually the reason he wanted to carry on. As you can imagine, losing an arm is a pretty devastating thing. Now, having two of them myself, having not gone through this, I don't actually know what the experience is like. But in listening to him, he said, I was a caregiver. I was the main supplier. My role, my mental role for the family was the supplier, was the caregiver. And when I lost my arm, I lost that role. And I lost my role in basically in life. I didn't know my position. And it was a very devastating situation. And many people we've talked to have said how devastating that is. And in fact, it leads to questions about whether it's worth going on or not, and if their internal value. But through that process, he would still go walks with his niece. And what he told us is that was some of the most important thing for him through that time, was when he was walking with his niece. We started working with him in this project. He said, the thing I want most, if you could replace from this hand, was that I want to feel my wife. I want to feel her hand. I want to feel my niece's hand. And he said, well, during this time when he was recovering, when they would go for a walk, she would never hold his intact hand. So he lost his left hand. He still has his right. Whenever they would walk, she would always hold the prosthesis. He didn't know why, but she would never actually hold his real hand. So he hasn't actually walked with her, felt holding her hand since the time he lost his hand. And that for him was like the biggest thing. And even, he says, my wife understands. And as much as I want to hold her hand, holding my nieces is the thing that I look most forward to. So this loss of connection actually becomes really important in somebody that's lost their arm, lost their connection. And I think what it brings out is this concept of that we are all about connection. And what we need to do is replace that connection in this case. And so we think about what is the, what's the goal of a machine that I need to give to replace this, is I need to replace communication. I really need to replace something that connects the individual to the person. And so this is an example in this whole technology relationship. I'm going to take an example for the rest of today that's very specific to person with limb loss. And so the technology we're talking about is the prosthesis here. This is it's basically a robotic system that's been built to replace the lost limb. And what we have is essentially this conjunctive, this connected relationship that we want to create is mutually beneficial. In this case, it's only beneficial to the individual. We'll move to more of this mutualistic as we get into next week's talk. But here, the prosthesis is providing benefit to the individual. And in our case, it's not just function, but it's also the sense of touch and connection. And so how do we get there? So this is what people want. As an engineer, I think about the technology. When I build a hand, we're going to build something that looks like a hand. We're going to do all these different things. But when you talk to people, they don't care about the engineering of the hand. They just want to not even think about it as being different than what it was when they had the hand in the first place. And so what we're really trying to do is develop this technology that moves on where the person doesn't think about their loss of hand, but in fact is creating this relationship where it's beneficial to them, this beneficial aspect, and the technology could care less. But it's this business about connection is the thing they want. So I'm looking at shifting the paradigm, this idea of not technology. Again, this has been around for a long time with prosthetics. I'm going to give you a bit of a background in a minute, but think about this not so much in prostheses replacing a hand, but also thinking about this idea of how technology and humans, this relationship, is working together towards this connected, beneficial relationship with technology, this intimate connection with the technology. And that's where the idea of connection to humans comes into this, as we're going to talk about for the rest of today. So before we begin our work, what is the state of the prostheses today? This is what prosthetics are. And from way back in the beginning of, of early upper limb prosthetics, World War I, that time of frame, basically they were harness driven. So you had a harness that would go around your shoulder, a prosthesis you would put on your limb, and basically as you would shrug your shoulder, it would open or close. You could set it one of two ways, this terminal device, which was a hook. This is not really an arm, but it was functional. It provided the benefit they had. And there were problems with it. If you reached over your head, this wouldn't work. The cables would go slack. You couldn't connect. But ultimately, this was the prosthetic system for many, many years. And then what came along are electronic hands. So they built these hands. This is an Autobach hand here that's a 3-jaw chuck. So it just opens and closes. That's all it does, which is all the hook did, actually. They made it to look human-like, started to make it anthropomorphic. Basically, you give it the human shape. And so in the last, I would say, 2 decades, since basically the conflicts in the Middle East, when DARPA took interest, they began to develop more humanistic hands. And while this one only had the 2 fingers and a thumb that moved, now hands are being developed where all 5 fingers can move individually. Again, we focused on the engineering of all of this, and this is an Autobach hand where they have individual fingers that can move. The B-Bionic prosthetic, which is now an Autobach device. Each of these fingers move independently. Other companies have the same thing. There's a group in New Zealand that has what's called the Tasca hand. And ultimately, the most advanced in the sense of capable from a functional perspective is by Mobius Bionics. It's actually a Dean Kamen's company that developed the Luke arm. If you've heard about that, this is what was developed through DARPA, this idea of the Luke arm. While these basically are hands, the fingers move. This has a fully articulated wrist, individual fingers that move, the thumb that moves, and an elbow, and as well as there's actually a full shoulder system. So that's the state of the art of prostheses, but you can imagine, how do I control all this degrees of freedom? And so this idea of control or agency over this in today's prosthetics, outside the arm, the strapping system, a myoelectric prosthesis, basically meaning reading the activity of the muscle, is showing in this picture here where this hand, this is a socket. So this is the hand I showed you earlier from Ottobock. The socket goes and fits on the arm. And then ultimately there's these electrodes, which are barely visible. It's not important you see them, but they're inside the socket that sit on the surface of the skin. And when the person thinks about doing something with their hand, say, for example, extending their wrist, there's activity in that muscle that can be recorded. And once that's picked up, that just basically is turned into a motor command to open the hand. And so a person thinks about extending the wrist, the hand will open. They think about flexing the wrist and the hand will close. So that's a pretty simple control, and it's not natural. So they have agency. They can control the hand. That's what agency means, is they're in control of it. But when they want the hand to open, they actually have to think about the wrist. So it's not a natural engagement. And it only has 1 degree of freedom, and these electrodes, as we'll talk about in the next section, are not very good. It's pretty hard to get any more control of individual digits with the type of electrode systems here. And so there are companies now that, COAP and different ones, that take many electrical readings off the surface of the skin and use these AI techniques. So they analyze the data coming out from the individual and make pattern recognition guesses. So if the person's doing something like this, multiple with their hand, they're guessing what they want to do, and then they can move all of the degrees of freedom into that configuration. So more sophisticated surface recording techniques, but they're still pretty crude. Basically, a person can do one activity, whether the shape of it might change. They can do things from maybe this grasp or pointing, but they can do one task at a time, and this system does all the work for them. So they're not really in control. And this idea of agency, that I'm doing what I want, is very important. This is an advance in terms of having these hands, but it's not the same thing as actually thinking about moving your finger and the finger moves. The other thing is, how do we replace sensation? And there's a lot of different ways that people have tried this, and none of them have been particularly successful. So the idea is, one thing they do, so imagine this is showing a person running a mouse, but if this hand is missing, you don't have the fingers that you can actually engage with. So people have developed vibrating motors, just like your cell phone. And depending on how hard the pressure on the prosthesis is pushing on the finger, they can vibrate this motor at different rates or different intensities. And the person can interpret that then as how hard they're grabbing the finger. And that actually works in the lab. They've shown some good results on that. When you take it home, it's unnatural, and most people don't use it. In fact, most modern prostheses don't use this. People have used other ideas, such as air bladders, where the pressure on the finger is related to how much air is pushed into a bladder on the forearm, or surface stimulation, where you actually put electrical contacts here, and when you stimulate, it's kind of like putting a 9-volt battery on your tongue, and you feel these little sparks on, not sparks, that's the wrong term, but you feel these little kind of pringly feeling on the skin. All of them work in the lab, and they have a sense of feedback. And the importance of this actually is related to haptic interfaces now. There's a lot of discussion about VR and gaming, where people are developing haptic interfaces. And in fact, we're going to talk a lot about that. And these are what people are trying to do, are very similar ideas. The problems with them is they're external. Or the challenges, I shouldn't say problems, but the challenges are they're external, they have a lot of wiring and things with them, and as well as they don't represent the actual feeling that may be in the hand or the finger. You have to consciously think about a vibration on your forearm related to the amount of pressure you push in the finger. And that has a lot of implications we're going to talk about in the next section here as to what's going on. And ultimately, at the end of the day, what people want is not to have, as I showed in the first picture, that diagram, they don't want to have a tool on there that they can use effectively. They actually want their hand back. And this is this idea of embodiment, or more importantly, incorporation. How does one take the technology and embody it, or incorporate it into their sense of self? So if you have a prosthetic system, you don't want it to be a tool that you're using, like if you use a rake or a grabber or something like that. You can control it, you're in control of it, but it's not you. What you want to do, and ideal, if we actually make this technology truly part of the individual, is we want to actually incorporate that into their sense of self. We want them to feel like it's part of their hand. And that's what we've been able to do. And the next part of this section, we'll talk about how we've been working towards those goals with the prosthetic systems. And then I'll finish this with the idea of what does this relate to our broader relationship with technology and what we can do.
James Lawrence is asking, so what are the ethical issues involved with this rather than technology? But you're talking about incorporation. I mean, Yeah, there must be people must have thought about the bioethics of this.
Yeah, so that is a great question for next week. And in fact, this is actually a very large component of where we're headed in this set of talks. But the ideas of the ethics of what we're doing in the prosthetics have not been as much of an issue, because ultimately people want to feel their hand, they're getting connected again. This question can come back to a little bit in how we're connecting at the end of the today, but the broader implications of what we're doing actually is a much bigger ethical question that I'd like to maybe readdress at the end of this talk, and particularly bring up in next week's discussion. I think that's there's a bigger picture that I think we'll address later.
Bernice asks, how does this new technology utilize microelectronics?
Right. So we'll talk about that in the next section, where we actually give you a specific instance of what it is. A lot of this is creating the communication schemes to how we talk to the nervous system. And so what we're going to talk about in the final section coming up is exactly that, of how do we take information that's a mechanical information, a system, a machine, and actually convert that into the neural language, into the sense of self, the way that the brain normally processes information, convert those two so they can communicate directly. What we're looking for, we're going to talk about in the next section, is the seamless integration between mechanical information that's interpreted as yourself, and how do you take biologic information and provide it back to the activity of the hand. And that's where the electronics come in. And we, in fact, are using AI algorithms. We use some of these same techniques to convert between the two domains. And that's where the microelectronics, the AI, all the things that we have using machines for comes into play, but in a symbiotic relationship where we're making this connection directly between human and machine, not in a competitive way.
I have a question here from Vivian7 that really sends us back to the first part of the talk, and we didn't get the chance to answer it then. What are we doing from a social sense as to how humans feel they're being replaced by machines? And does that have application also to the augmentation of people? Presumably that's going to allow fewer people to do the work of more people, for example. And so people, again, will be replaced by machines, even through this augmentation.
Yeah, I mean, I think that's a great question, broader than a simple answer here, in the sense that there are many dimensions to that very question. And I think that we're just beginning to scratch the surface of it. The way the society is handling it is, you have things from people that, even talking about addiction to phones, addiction to the internet. There's things about how technology is engaging us in different ways. We all talk about this with how our kids communicate very different than we used to. They're very technologically oriented. But we're also, needing to look to the future. Sociologically, we have things in the media that are, the few examples I showed from movies of 15, 20 years ago, or even now, if you watch Netflix, there's this exploration through the idea of Black Mirror. And while those aren't scientifically, necessarily explorations of it, they are the way our society deals with it. And what you'll often see is that, technology creates a threat initially, and then there's a part of it that likes to play in that. And I think part of that is, we're inclined to think about the negative. And so Black Mirror sells. People watch these dystopic views of things. But I also think if you look back to, say, Arthur Clarke in the 2001 Space Odyssey series, and other writers that were much closer to science, there's an exploration of what it could do in how we work together. So I think these two things, we have to look at it from a psychological perspectives, and actually that discipline, which I'm not, so I don't want to give a whole lot of answer there. How do we explore this relationship with technology? And then in terms of what are the societal and economic costs, I think we all have to look at how we're going to evolve as a society. It's just like, again, I think back when you look at early cars, there was a recognition of there would never be more than 1,500 cars on the road because there's only enough chauffeurs for 1,500 people. And of course, that's completely changed as well. So I think the challenge comes down to many ways with technology is a fixed mindset versus an open mindset of looking to what the future is. And there's always a conflict between those two things when we talk about them.
And as we know, the head of IBM said there was only market for 3 computers, right?
Right, and Bill Gates said 640K is enough for anyone.
So a final question in this section, and it's not really a question so much as a comment, but I think maybe it leads into some of what you're talking about. Kingman Stroll writes, there's a limit to human calculations in real time. For instance, in clinical decisions, the human usually picks by experience or whim at most 5 variables, when there may be 10 or more with 5% effect in each combination that are more important. So how does that play into this idea of of combining the human and the machine.
Yeah, and I think this is a perfect example, actually, and thanks, Kingman. I think this is the case where actually human and technology work much better together. And so the advantage of technology is that it can not only 3 to 10 variables at a time and look at them, it actually can look at the data from, with our connected world, we can look at the decisions and outcomes from everywhere around the world, right? Everybody that's connected, the action and consequence of everything that happened can be analyzed on the computers and look and making these correlations, right? But there's no 100% between them, and there's all these interesting use cases. So I think that if you put the human intelligence, which is very good about, speaking of extrapolation earlier, we're very good about looking beyond what the data directly says and bringing in factors. The computer's only as good as what you program into it to look at, and the computer cannot look at the entirety of life. And so as a physician, and again, I apologize if I misspeak, but my understanding is there's an importance for the person, getting to know the person and understanding their environment. And there's things that don't show up in the data that may show up in your decision-making process. If you could feed the computer every bit of data, maybe we have something there. So the computer works with lots of data, but only what you feed it, where a physician has other things that work together. There's been a recent thing with this. I just saw an article recently where they actually put this to the test in the fashion industry. And so they used AI to guesstimate trends of the future and do buying for a given store. And of course, the buyers that normally do this, their expertise, said, we can beat the computer. And then they had this competition, and the AI put together and actually beat the buyers in a head-to-head very handily. Very handily. And so then they said, okay, well, never mind. If we hear from the machine, so let's take this idea of what the machine is saying, we'll use that as our as a advisement to what we do, and then we'll make the decisions versus the machine. Machines still alone beat them versus them taking decisions on that. However, and this is where I think the really interesting part is, when the human and the machine work together, right? So the data for the human's putting in sort of what we're good at, these other observations, the other pieces around this, and they work together in a combined way, a symbiotic manner. And then there was a final decision that was put out from all the data, including the human experience data. Then that beat the machine alone or the buyer hand down. So we have to figure out what that relationship is. And so I think we're beginning to understand, how does the human experience, the human data, and what our brain actually does in combination with the way that the computer works, how to make that work better. And so I think these are great questions about how we begin this engagement, but rather than making it a competition, I think we start to look at exactly that question of, what can I do? What do I bring to the picture that's not chomping numbers? And what does the computer bring that is pulling data that's far more than I can store in my brain in any given way? And so I think if we recognize the value of the computer for taking lots of data and analyzing it in ways that we don't think, and again, I'll go back to the calculator example. The first TI calculators crunched numbers way quicker than I ever could. But that didn't mean it was more intelligent than I. It just had a different thing that I could use in a way to my benefit and to our benefit, machines and humans. So I think that's what we have to be thinking about, is what is it that we can add to each other to make that work? Now, what I was talking about is, this is what the person wants. So how do we achieve that? And what I gave you a little bit of introduction to in the last section is that the machines that we have now, the prostheses, were limited in that. And the reason was that they weren't really connected to the individual. And so what we want to do ideally now is actually take sensor data and send it directly to the brain. Or we want to take brain's activity and send it back to the arm in a very natural, connected way. And what we're doing, the system that I'm going to talk about now and the work we've done, takes sensor information from a prosthesis, so mechanical information from a machine, runs it through our system, and this is where the science is, what does this system look like? So I'm going to talk about what we've been doing to understand this box. But ultimately take that data, convert it from mechanical language here to neural language here, stimulate the nerve that remains in the arm. So when you've lost the hand, all the sensors and the fingers are gone, but the wire that used to connect them to your brain is still like one wire that runs up. And so where it's left in your arm, we can actually tap into that. And through, the way tools and techniques of neural engineering, which I'm not going to talk about here, we can actually cause that nerve to activate. And if we do it properly, what happens is that information goes up to the brain. And what I'll show you, but in theory, when we started this, is that the brain then interprets it to be their hand. It doesn't know that I artificially generated it. It just says, hey, that's my finger. And when you see the finger touching an individual and feel feel it simultaneously, now we get this idea of vision and tactile together, this idea of visual tactile synchrony, that the brain begins to equate that information with their actual hand, which is the model it knows. And conversely, we want the brain, it sends down commands. So many of the muscles that move the hand are actually up in the forearm. So if you lose the hand, you still have these muscles here. And then, so when you think about moving your finger, the muscle that used to move the finger is actually activated, and you can move the finger. And so what we do is we interpret that information, we pull that out of that muscle system here, convert that from neural or from biologic data, muscle data, into motor commands to actually make the hand move as you intended your actual hand to move. That's the concept, and that's what we're working to do, and what we've been doing for the last 10 years. This shows you the basic technology of this. And now, again, I bring in this idea, we were achieving this endosymbiotic, the human, the technology directly integrated. And we're benefiting, in this case, it's still just benefiting the individual. So we're not to the full step of this mutualistic part, but with the benefit is to the individual, where we're connecting directly through what we call nerve cuff electrodes. So these are things that I've developed in my PhD and worked on to how do I put it on that nerve, that wire, and through multiple contacts, through these little electrical portals, so I can put current through each one of these, I can activate small little parts of this nerve that in our case might feel like part of one finger, or if I stimulate another one of these little electrical parts, another finger. And so that way that if there's information here, I can transfer it through this, which then directly connects to the nerve, this endosymbiotic relationship that conveys it up to the brain that we hope will produce, and will show you produces this idea of touch. Conversely, we take information from the brain by recording this muscle activity. So my colleagues, well before me here at Case Western Reserve University, developed these electrodes that can place directly in the muscle, and these things last for long periods of time, and record the activity. We pull that out and record it, and then use that to drive the prosthesis as though it were their hand. And so this is what I'm going to show you, what we've been working towards, the first version, and where we're headed in the second version, and then what that implies for what we want to do down the future. So this is now putting it in this idea of still basically the human's benefiting technology is still there, but now we're directly connecting to the human. So rather than all these surface things, we're directly connecting into the human at this point here. So have we done this? We have. And so we have more than 7 years where a system where we're interacting directly with the nerve has been implanted. So we have these electrodes I was showing you before. This is the same picture actually, connected to the nerves. And in the first subjects we did, we only did the sensory part. So we only restored sensation to these individuals. And those have been for over 7 years. We have 2 subjects that have been implanted, and they're still going today. They still come into the lab regularly when we aren't locked down. These have all been, in both of these, I'm going to talk about all 3 of these different subjects. The leads come through the skin, and we're going to show you where the technology and the microelectronics has driven us to get rid of this down the road. But right now, it's just basically a mechanical wire going from the nerve out through the skin to our external stimulation devices. And that's how we interact with the human at this point. And this is the one then for we have over 2 years of experience with somebody with both the neural interface for sensation and also these recordings from EMG for different control. And we've also done this for the lower extremity. So I will talk a lot about for the upper extremity, which is predominance of my work, but I work with Ron Triola and Hamid Shakar, who do this for the lower extremity in their team. And now we have 4 years at least with at least 3 subjects with these electrodes implanted to restore the sensation to the foot, which is now lost from a lower extremity limb loss. Just to give you a sense of how we look at this, so people were asking together earlier, what are the types of questions we try to address? This is this pyramid sort of lays out the way that we think about this problem. You know, our research goals overall, and I'll talk about this in a second, but our research goals overall is to develop this maturing technology. So within the next 10 years or so, we hope to have this technology matured enough to make it broadly available, not just in the lab. And there's a lot of work to do that and a lot of regulatory along the way, et cetera. But that's kind of the time frame we're hoping. And I'll show you why at the end of the slide. But really what's important, if you go back to what I was talking earlier about connection and touch, is the psychology of the human-tech symbiosis. So while we're doing this for limb loss, as we think towards next week's talk and where the broader picture is, we're starting to understand the psychology, the connection of the human to the machine. We also want to understand multimodal processing. So if I'm seeing something and feeling at the same time, does that change how I interpret? And we really understand the neural physiology of how I communicate. This is that language translation I was talking about earlier. How do I take mechanical or machine information and turn it into neurologic or human information? And we developed that through these, so this is our sensory side, where the bottom very simplest layer is if I have a finger and I feel just the fingertip, how do I convey information about touch at one point? And I'll talk about that in some detail. And if you move move up, if I start having multiple places of sensation, how does that relate? So if I grab a cup, for example, it's not just that I feel fingertip pressure. It's that the rate at which I feel pressure on each of the different fingers and how they come together makes me realize that it's a cup versus a plate or something of that nature. And so this is building up sensation. On this side, this is recording from one single muscle, and then we get to multiple muscles to get complex activity. And then we get to the level of integrating them. So as I feel my finger touch, I can modulate the force on the motor side. So this is integrating the sensory motor together. How does that affect performance? And then importantly, these are all lab type of activities. Does it matter in the home? If I send the person home, does it actually change their life? Do they actually feel better about, do they feel like they have a hand? And how does that change over time? So this is the framework with all the work that we're doing in the lab. And I'm going to talk about a couple different things and how they work. And I'll go fairly quick through this for the time, but I want you to see how they're related to what we're doing in connection to the technology. So we'll talk about touch and proprioception. That's basically what I feel when I touch something in the position of my hand or my fingers and my arm. Agency, which is the ability to control. Multimodal engagement, and I'll explain that a bit more later. Neural engagement, and so how we connect across the whole neural axis, and control we'll talk about. Use at home, and then what this relates to learning. So these are the main topics I just wanted to introduce briefly to you. So let's talk about touch. There's 4 types of things about touch. There's where you feel it on your hand. There's how hard you feel it, so the idea of intensity, how much pressure I'm feeling on there. The idea that it adapts over time, so if you're wearing clothes, they don't drive you nuts because you begin to adapt that sensation, you begin to not feel it. And then the quality, what does it feel like? Is it silk? Is it sandpaper? Is it paresthesia? What are the feelings? And so all of these together, we have to learn what is that language from, if I touch with a prosthesis, how do I convey these characteristics of touch? And more importantly, our question was, can I convey them? And what we've seen is that by stimulating through the techniques we have, and there's references here if people want to look for this paper, the details, but essentially we know we can produce location that's on the fingertips of the hand, all around the hand. So we can produce location, very selective location about where it is. We know the intensity we can actually mimic. So fine touch versus heavy pressure, we can in fact control stimulation in such a way that you can have the same gradation and perception as you can with the normal hand. It does adapt. So you don't need a hand to have this adaptation. I mean, there's some broader perspective that's going on. And we're learning how to change what it feels like. So we can stimulate one way, it might feel like a tingle. We stimulate a different way and it feels like a touch. And so we're beginning to get these ideas of quality in there. So our stimulated characteristics, the connections that we make with the machine, has characteristics that are similar to the way the individual normally felt their hand before. That's an important piece. Proprioception is the idea of knowing where you are in space. So balance is an important thing with this. Knowing what your ankle is and where the space of your arms are is all related to that. We are able to produce that, and I won't go into a lot of details, but we get, people will, when we stimulate different channels than touch, they'll feel their hand moving, they'll feel it tensing together. It's very useful to know if they're grabbing an object, whether their fingers came together and touched, or they're grabbing an object. You have to know if the hand is still open or closed. And we're still looking to understand the language and how this is working. And so I won't talk about this in great detail, but there's research still going on. And what is it that we're getting with proprioception and how? But we do know we're getting proprioception. And that's still a tricky thing. It's a complex sensation that if anybody's familiar with it or wants to talk about it, we can talk about. We start about thinking about multimodal sensory integration. Think about this from the concept of if you have one perception of the world. If I think about things, I only have one perception. It's not like I can feel 10 different things. I mean, I feel 10 different parts in the hand, but I have one recognition of the world. And so what the brain does is it takes your visual input, it takes your tactile input, it takes all the information, and makes one perception of the world. Visual illusions, optical illusions are a great example of this, where one perception, your vision, is different than what's actually maybe in a different perception. And it tells us that the weighting, people do a lot of research looking at the weighting of one input stream, maybe vision versus tactile. So we started to look at some of these aspects. Grasp recognition, we looked at whether or not a person can tell what their hand is doing without looking at it from the sensory information coming back, and how does it affect tasks. So this is the grasp recognition idea. And so what we do in this experiment is we put the hand where the user can't feel it or see it, but we give them the information coming back. So they feel all these sensory points. The green shows where if they're grabbing this type of, if the hand is in this situation, they may or not feel the fingertips such as this. And the red show the ones they're not feeling. So depending on where the hand is, different sensory information comes in. And we ask them to tell them what the shape of the hand is. And they're very accurate in doing this. And in fact, we train them on 4 parts of this. They learn different things, but they're able to interpret new grasps because they have an understanding of the hand and its position and how new information is going to relate relate to different grasp patterns. And so they use this, like if you feel something novel because of what you know of your history, you're able to use that information for the hand. And so they're able to integrate this multimodal integration, these multiple domains for hand grasp detection is one example of what we're doing. We did similar things in the foot. And so we would have, and it's really interesting how the sense of vision connects with the sense of, again, this perceptual reality. And so what we did here is that there were sensations that when we just stimulated, so we weren't doing anything, we just asked the person what they felt. When we did the connection to the individual, the stimulation, they would feel it on their toe. And what happened is if we then pushed their toe when we did the stimulation, they saw visually and they felt it at the same time. And what happened is the response to being the toe went up. So the red is like a more response to being their toe. So when they're visually congruent, they meant the same, the response went even higher. So they learned, they associated these connections. Interestingly though, when we made them visually incongruent, so the same channel that may have been the toe one time, when we started pushing their heel but gave them the toe, they actually started to respond as though it was the heel. So this is the idea of when you see something and you feel something else, these two conflicting pieces are relearned or reconnected, and the vision tends to take the lead in a lot of these cases. So it was actually quite interesting that the map is not static. You begin to learn to interpret information from all the sensory information that's coming in. And even if some of it's artificial, you still incorporate that into your schema, into what you learn. The other thing we looked that were like reaction time. So if you're doing something, for example, we gave a test where we're looking at a light, and their only goal was to close their prosthesis as fast as they could. And they either saw the light, they felt the tingle, felt the touch on their finger, or they saw both together. And in all cases, light was slower by about 100 milliseconds. And so starting to think about this, that means that you feel things and react. It's kind of like touching a hot stove and pulling away. You get that before you actually feel it. Now think about it, if we actually use this information, say if I'm driving a car, for example, and this is a case where maybe if I'm driving the car, if I felt it, I would respond quicker and maybe save myself in these examples. So the whole point of all this, and from time I won't go into great detail, but ultimately that information is processed to not just that they feel at their finger, but it's actually processed in all the neural pathways that exist. And that's an important thing. So we're artificially putting information in, and it's integrated in these pathways. And so we're actually integrating with the user's capabilities. We reduced dependence on vision. We did the test. This is this kind of sensory motor connection where we wanted them just to pull the stem out of a cherry in this case. And ultimately what they did is they would feel the sensation, and even if they could look at the cherry but didn't have feeling, so if we weren't giving them the sense of touch, when they pulled the cherry stem, they would almost invariably crush the cherry because they put too much pressure. However, if we gave them the sense of touch, even if we blinded them completely, all they could do is feel with that sense of touch we've been providing them, they'd never break the cherry. And so ultimately they gain, just because we provide this feedback, we change nothing about the control scheme. They were able to finer modulate that force and do more complex, precise tasks with this feedback. So again, they're getting this connection, they're beginning to work with the hand. And in here, we started talking about the controls. Now, if you remembered, I talked about the idea of the sensory stimulation initially. With these EMG channels, what happens if you do it from the surface, ultimately, only thing that's important about this diagram, it's a parallelogram, but ultimately what we wanted is that each channel only records from itself. And so we'd have everything being black and just down the middle being white. And if we have the surface recordings, you see a noise across them. We can't pick out individual signals. But by moving this integrated connection to the human, we actually can pick out very clearly individual signals. And what that means is we can get better degrees of freedom, more control over the hand. And ultimately, when a person thinks about moving an individual finger, we can pick that out in a much better way than we can with these surface devices. So it's giving us better control by connecting directly to the human is the key point here. I want to talk about the real world and the going home component. So we did all this stuff in the lab. What's it actually matter? If I take this arm home, do I actually use it? Does it make a difference in my daily life? And what we saw, again, because I don't want to take too long on this, is that within a week, so if they had it home for a week or less, their quality of life went up. We took a bunch of surveys. We did a whole bunch of assessments, psychophysical assessments. Their quality of life went up. Their self-efficacy, their embodiment, they felt like they had their hand back. They were becoming two-handed again. They had social touch. They would hold somebody's hand. They'd hold their wife with that hand as opposed to their other one. Their body image would improve, and the prosthesis efficiency, how well they used it, would go up. And not only that, the important thing is the location refined. So they would become more tuned to where they were seeing the touch. So even if they were broader perspective before, it got refined and it became more natural, it became less tingly, it became more like their hand touching things. So this gets the idea of over time, they actually learned because we're connecting to that nervous system, it became more and more their natural hand. And this is just showing some of the actual data. We see is less than a week, we had significant jumps in all these different measures that we did and essentially became much more of their arm and using what they're doing. I will show the next video. This is our subject talking about this experience. And I apologize, it's from the lab, so it's not super easy to hear, so I'll be quiet. But I want you to listen to what he says about his experience with the hand.
Sometimes with the sensation though, you know, being able to feel that I've grabbed it, I'm holding it, the bend sensor, because it feels like it contracts, feels like it's reached in, grabbed around things, and then feeling it in the fingertips and everything. Makes a big difference. The 2-year-old, she come up to me and be able to grab her and be able to feel, when I squeeze just a little bit to feel, okay, I'm not squeezing too tight to pick her up and then bring her up this way. Just kind of amazing because I've never been able to feel with the right hand.
So when you were actually using it then the rest of the 8 hours,
I never even.
were you thinking about it? Did it feel unusual? I mean,
Didn't even look at it.
so how did it, but in
It
use?
seemed more natural. It seemed to feel more natural.
Okay.
You know, I knew when it was off, it was off.
These things can be a little.
When I started doing stuff, it's like, okay, that's my fingers. So it felt like I was using more of a hand than just prosthetic.
I says, well, it's nice. It's nice being able to feel your hand and be able to do things. And I have to watch as close because I have an idea how hard I'm grabbing things. And I said, things gonna suck. I says, tonight's my last night with it. When I come back, I said, I got to wear it another 3 weeks, but that'll be without sensation. I says, you know, that's like losing your hand all over again.
Yeah. Yeah.
Because I've been more apt to wear it and more willing to wear it, being able to feel that sensation.
So this idea of losing the hand again, I think is really powerful. And one more short video, this is less than a minute, but I want you to get, this gets across the importance of the touch component of what it is from this subject.
She comes through the door, so she reaches out and
He's talking about his wife here.
she grabs my hand. And we hugged. I grabbed her arm and I petted it just so I could feel her skin. I was whole. I was complete. This is a tool. When the system's turned on, it's mine. It's my hand. What the system done personally for me, it takes the touch and turns it to an emotional feeling, a physical touch to an emotional feeling.
I think this is the important part, that this is now becoming a connection, an important thing. So just to finish up the last couple slides here, last couple of things we'll talk about. The question earlier about how does electronics enter into this? For the last 4 years, we've been working with Medtronic and Lawrence Livermore in various labs to develop, where all those wires went through the skin, all the external parts, we now have a pacemaker system that has twice the number of channels to communicate to the individual from the sensory side and twice the number of channels to get information. It's fully connected by Bluetooth. So rather than have stuff external, basically they can now connect that system through their phone to their prosthesis and basically to the world, as we'll get to in a second. We have FDA approval to begin IDE trials, a 15-subject randomized clinical trial to get us one step closer to moving this forward. But just to move on and foreshadow a little bit, and then I'm going to end this for now for questions. I appreciate your patience. It's all about connection. You heard this in the video. I only used my remaining hand because he was worried about hurting her when he didn't have sensation. With sensation, picked her right up. And I think this quote is really where I want to jump off for to move forward. The subject would say, my prosthetic with no sensation is a tool at the end of my arm. With sensation, it is my hand. And that's a critical thing, because if I took that prosthesis off and placed it anywhere in the world, the same information being transmitted digitally would still be his hand. And so ultimately, we are now saying that experience of a hand, the experience of being a human, is a digital process that I can transmit over the web. And that idea is quite significant. Ultimately, we're creating this idea of neuroreality. What I'm going to leave you with, this is my last slide, to think about for next week as we talk about this. We're now connecting to the senses in a very direct way between the machine and the human. If you think philosophically back to this whole idea of what it is that we do, so even though people talk about stimulating the brain directly and everything we do from birth is given to us through our senses, from the Kantian view that everything I know, all of my knowledge begins with the senses. And now that we can actually provide senses, whether from a machine or for otherwise, we can now start to think about this as a transformative evolution of the relationship that's the connection between the human brain, technology, and ultimately society that would enable our mind to transcend the barriers of the body. I no longer need a hand and touching with a hand to actually have this sense of touch. I can move it across the world and transcends that barrier of the body to make me connected at a much grander scale. And we'll talk about that next week and what that could mean, and that's where we want to go. And with that, I thank you for your attention. I'm happy to talk about whatever you'd like to talk about, and thank you.
I'll clap for everybody.